Hi there, my name is Greg Staples. I'm the sales manager for spectroscopy products at BaySpec. I'm here at Photonics West 2017, and today I'm going to be discussing hyperspectral imaging. On a previous video, I did an introduction to hyperspectral imaging, talking about different types of imagers, be it snapshot, be it push broom, different reasons to do different wavelengths. Today I want to take that a little step further and talk about specifically why you would select different wavelengths, and in this case, the near-infrared. So, for example, in precision agriculture is a very important application for hyperspectral imaging. It's typically done in the near-infrared, looking at a ratio of some red to near-infrared. In the near-infrared portion of the spectrum, you get a lot more fundamental information than you get in the visible spectrum, because in the visible you're looking at an overtone, where in the near-infrared you have more fundamental modes and giving you a lot more information. So for precision agriculture, typically what they're interested in is nitrogen content, water content, carbon content. You can capture some of that in the visible, but you get a lot more of that information in the near-infrared. Also, another example is food sorting. So you can look at near-infrared there and you can get some good information, but if you want a good penetration depth into your sample, it's much more efficient to use shortwave infrared. An example would be sorting apples. Looking at it visibly or even in the near-infrared, you might not be able to see the bruising inside of the fruit, but if you switch into the shortwave, you get a lot more information there. Other examples are mining. So there's a lot of information on the minerals in shortwave, be it from 1100 nanometers all the way out to 2500 nanometers. Typically, they're beyond 1700 nanometers, and so you're looking for fundamental minerals to be able to know whether you want to mine in a certain area. Another good example for shortwave is pharmaceuticals. You're looking at counterfeit pharmaceuticals, looking at the quality of the drugs or the pills. So shortwave is a very powerful tool for hyperspectral imaging, but traditionally it's been very expensive and very heavy. That is due to the fact that you're using a different detector in the shortwave infrared than you are in the visible. In this case, you're using an InGaAs detector. InGaAs, they are not as high resolution. They can be noisy, especially if you go out beyond 1.7 microns out to 2.2 or out to 2.5. And so that has limited a lot of the applications of this technology. Now at BaySpec, we have developed a new sensor. It's still an InGaAs detector, but a new hyperspectral imager that goes from 900 to 1700 nanometers. It's much smaller, much more compact, and it allows you to get into these applications that you wouldn't be able to get into otherwise. It's basically the size of our handheld hyperspectral imager, and it's very light. It's 800 grams, and as I mentioned, it goes from 900 to 1700 nanometers. So it's a very good example of a product that, as technology improves, things become smaller, things become cheaper, and much more able to look at new applications. Thank you for your time.